few days is going to be on indeterminate forms, things that previously we have not been able to evaluate limits of. So this section we actually kind of skipped. We already covered 4.5 and now I'm going backwards to 4.4. The book had this section first because some of the problems in 4.5, when you tried to do your horizontal asymptote, the limit as you approached infinity, they didn't work. I only gave you the nice ones for graphing purposes, and now we're going to talk about how we would have evaluated those that we couldn't have otherwise. So, if we were trying to look at a function like this, the natural log of x over x minus 1. Okay? We would all agree that you can't just plug a 1 in that. But we could still talk about the limit there, because we know that a limit is the behavior as you're approaching it, not necessarily what just happens at the point. So I could ask you about the limit as you approach 1. Now, if we had just tried to do our limit laws, we have a problem. You can't plug it in because the bottom's 0. Some of our other rules, like dividing by the highest power of x, is that going to work with a natural log? No, so that doesn't work. We could try reasoning through it, but it's not even just a one-sided limit. So sometimes if it's just approaching from one side, we might talk about, plugging in very small numbers, getting closer to 1, but it's a two-sided limit. So we couldn't really do that. However, would you agree that if we just plugged 1 into that, both the numerator and the denominator would be 0? The natural log of 1 is 0, and 1 minus 1 is 0. So this is what's called an indeterminate form, 0 over 0. If any time you go to evaluate and both the top and bottom are 0, we have to have another option of doing it. There are two indeterminate forms that we're going to look at. We have done some already when we did our dividing by the highest power of x, but like I said, this isn't an option for that part, for that problem, so we have the other. So here's L'Hopital's rule. If f and g are differentiable functions, and the derivative of g is not 0, then if the limits of both f and g are going to 0, or they're both going to positive and negative infinity. In other words, if you go to evaluate this and you were to plug in, you get 0 over 0, or infinity over infinity, or negative infinity over negative infinity, or positive over negative infinity, anything like that, 0 over 0 or infinity over infinity, that's an indeterminate form. So what we will do instead, L'Hopital's rule tells us we could actually do the limit of the derivatives of those functions. Now, you want to be cautious. This only works in these indeterminate forms, so if it was actually 0 over infinity, and you tried to do L'Hopital's rule, you could get the wrong answer. So you don't want to use it unless it matches exactly. When you're doing these derivatives, it is not a quotient rule. You're just going to do the derivative of the numerator divided by the derivative of the denominator. So let's look at one. The one that I gave you. The limit as x approaches 1 of natural log of x over x minus 1. First we check. If I just put 1 in there, natural log of 1 is 0, 1 minus 1 is 0. So this is an indeterminate form, 0 over 0. So what we do, we will use our L'Hopital. I would like for you to denote when you use it, so you can write that you're using it. What I do most of the time is I just put an equal sign with an LH over the top, telling you that I've done L'Hopital's rule. And it says, since it's 0 over 0, we can do the limit as x approaches 1 of the derivatives. What's the derivative of natural log x? over the derivative of x minus 1. So we get the limit as x approaches 1 of 1 over x. And now you can plug a 1 into that and you get 1 for your final answer. So this allows us to calculate limits that we wouldn't have been able to before.
Okay, so this only works with functions that are undefined.
Not undefined, in indeterminate form. So 0 over 0 or infinity over infinity. Alright. Let's try some more.
So there was an answer, but we just weren't able to calculate it.
Right. The limit laws we had to this point weren't sufficient to find it. So this one, if I try regular limit laws, there's really not much we can do. Let's see if we just plugged in e to the infinity is just going to infinity. Infinity squared is going to infinity. So it's infinity over infinity. That means we can use L'Hopital's. So derivative of the top over derivative of the bottom. Derivative of e to the x is e to the x. Derivative of x squared. Okay. Now if I plugged in, e to the infinity is infinity. 2 times infinity is infinity. This is still infinity over infinity. What do you think we need to do? We're going to do L'Hopital's again. Do the derivatives again. Derivative of e to the x, still e to the x, but the derivative of 2x is 2. So now we get infinity over 2, which is infinity. Is that okay? Why don't you guys try one? In the last chapter. So.
We did take on courses.
We've done, yeah, maybe some. Okay, so if we just plugged in natural log of infinity, what's that going to? It's going to infinity. If you need to, you could look, remember your natural log graph, it looks something like this. So, you can use your graphing calculator if you forgot that. We did graph those back in college algebra. So this is infinity over the cube root of infinity is infinity. So we're going to do L'Hopital's. Okay, natural log of x, the derivative of that is 1 over x. The cube root of x, that's x to the 1/3, so it'd be 1/3 x to the negative 2/3. Now, we could do a lot to clean this up before we actually figure out if we can evaluate the limits. So let's start there. This is like 1 over x over 1 over 3x to the 2/3. How do you divide fractions? Flip and multiply. So 1 over x times 3x to the 2/3 over 1. Okay, so then if we simplify this, if you have x's on both top and bottom, you can subtract their exponents. So we end with 3 over x to the 1/3. So if x is going to infinity, that's 3 over infinity, which is 0.
Well,
like the answer.
No. Did you? Alright, so the next one, I'm gonna throw some tricks. So, limit as x approaches 0 of tangent x minus x over x cubed. Is it? I don't know if you tell me. What's the tangent of 0? 0 minus 0 over, so yes, it's 0 over 0.
Well, I was kind of confident until you said, I don't know.
So then we can do L'Hopital. Alright, derivative of tangent. Minus derivative of x over derivative of x cubed is 3x squared.
this is a formula.
Mm-hmm.
What is it?
It would be
Is it tangent?
Yes, it's tangent. I think it's tangent.
I'm impressed you recognize it as a formula.
Tangent.
Makes me happy.
Oh wait, it's in my other binder. Tangent.
So, yes, we could simplify this using our identities from trig. Yes, it's the tangent squared. But if you didn't recognize that, we could just keep trying to evaluate it. If I put in infinity, secant, oh, it's not approaching infinity, it's 0, isn't it? Actually, I can't put in infinity here. Alright, secant of 0. Cosine of 0 is 1, so secant squared would be 1. Minus 1 is 0 over 3 times 0 squared is 0. So I can't plug in yet. So what do we have to do? Same thing. Alright. Look, we get to use chain rule this time.
How come?
Isn't this fun? So, secant squared. So the 2 comes down. Inside stays the same. Subtract 1 from the power, so now it's to the first. Times derivative of the inside. What's the derivative of secant? Mm-hmm.
I don't remember this today.
Oh, I don't know.
How do you not remember it? I taught you these things.
I'm sorry, I guess I'm just not thinking.
Alright, what's the derivative of 3x squared? Okay. This is not looking real pretty, is it? We could simplify. This would give me 2 secant squared x tangent x over 6x. Okay, if I go to evaluate this, secant squared of 0 would be 1. So 2 times 1 times tangent of 0 is 0 over 0. Do you guys want to keep doing L'Hopital's, or do we want to think about if we have any old tricks?
Well, if we go back to the first derivative, what would happen if it was changed into tangent?
We would have actually ended up at the same thing.
You might as well just do L'Hopital's because we're saying 6 on the bottom.
The next time we will just get our 6 on the bottom. The top is going to get a little ugly because we will have to do chain rule and product rule within there. So that could get ugly. We also could do this. We've simplified some things like this before. To get to sines and cosines and start simplifying from there, and that's not a bad option either. So, what do you want to do?
Simplify again.
Simplify, do the law, whatever it's called.
No.
Cosine.
L'Hopital's?
It sounds like the hospital is about to put me in a hospital.
Okay, so take a vote. Who wants to do L'Hopital's again?
Okay.
Okay, a couple of you?
Let's just do it, I don't care.
Just do something.
Just do something. Nothing, make it.
Alright, let's try cleaning it up. Secant is 1 over cosine squared. Tangent is sine over cosine. Okay. We can
We're just
yeah,
simplifying
I got
it.
it.
I could reduce my 2 and my 6. Right, so I've got the limit as x approaches 0. 2 over 6. You can drop one of those. So we would get a sine x over cosine cubed. This is like over 1, so I could write that as 1 over 3x. Does anybody recognize something that we used to use?
Yeah.
Even,
What if I rewrote this? I put sine x over x and 1 over my free cosine cubed x. Okay, I just reordered them, but do you remember? Sine x over x, we used to have a rule. The limit as x approaches 0, sine x over x is 1. Times 1 over 3, cosine of 0 is 1. And we get 1/3. So don't just abandon all of your old limit laws. They do still come in handy. If we had done L'Hopital's again, we would have got there, but it was going to get really ugly in a hurry. So sometimes, especially when you're dealing with trig functions, the more you do the derivative, the worse it's going to get. So if there's another option, like sine x over x, that can save you some time. Alright, question 6. Limit as x approaches pi from the left of sine x over 1 minus x. What's the sine of pi? Zero. Over 1 minus, what's the cosine of pi?
1.
Close.
Oh,
Think about it, guys, if on your unit circle, pi is right here, that's the point -1, 0. So sine is 0, cosine is -1. You knew that.
I keep forgetting.
Okay, if you think about on the unit circle, this is 0, 0, so this would be the point -1, 0. Here's your 0, pi over 2, pi. Remember on the unit circle, your cosine is your x and your y is your sine. So sine of pi is 0, cosine pi is -1. So, can I use L'Hopital's here? No, do I even need to? This is just 0 over 2, which is 0. No L'Hopital's needed. So there might still be some that you can just evaluate to make sure you're paying attention. And not just doing L'Hopital's on everything. Alright. Let's get out our books. Open up to page 305. volunteer to read just that little indeterminate products? Towards the upper middle part of the page, just that little paragraph.
I'm gonna talk one more time. If the limit of, as x approaches a, of f of x equals 0, and the limit of x as x approaches a, of g of x equals infinity or negative infinity, then it isn't clear what the value of the limit as x approaches a of f of x, g of x, if any, will be. There is a struggle between f and g. If f wins, the answer will be 0. If g wins, the answer will be infinity or negative infinity. Or there may be a compromise where the answer is a finite non-zero number. This kind of limit is called indeterminate form of type 0 times infinity. We can deal with it by writing the product fg as a quotient. Fg equals f over 1 divided by g, or fg equals g over 1 divided by f. This converts the given limit into an indeterminate form of type 0 over 0 or infinity over infinity, so that we can use Hospital's rule.
Okay. So, what this is saying, we've been talking about what the indeterminate quotient looks like, 0, 0, or infinity over infinity. But if you're doing a product and you get 0 times infinity, you don't know what the answer is going to be. It's based on whether it's approaching 0 or infinity faster. So to do those, we are going to have to write them as a quotient so that L'Hopital's is an option. So to write it as a quotient, you will move one of them to the bottom and put it as the reciprocal. So for instance, the limit as x approaches 0 from the right of x natural log of x. Alright, if I'm just looking at this, as we are approaching 0 from the right, x is going to 0, the natural log, we've already talked about, the graph looks like this. As you're approaching 0 from the right, this is going to negative infinity. So we are going to rewrite this as a quotient. Would you rather put the reciprocal of x or the reciprocal of natural log on the bottom? Probably the x. So we'll do natural log x divided by 1 over x, because we can't change the problem. Okay, now the top is still going to negative infinity. The bottom, 1 over a smaller and smaller positive number, is going to right, the x is approaching 0, so 1 divided by that number. So like 1 divided by 0.1, 1 divided by 0.01, 1 divided by 0.001. It's going, yeah, it's getting bigger and bigger. As the x gets smaller, 1 over that number is getting bigger. So this is infinity over negative infinity. So now we can do L'Hopital's. So the derivative of natural log is 1 over x. The derivative of 1 over x, keep in mind that's just like x to the negative 1. So it'd be negative x to the negative 2. Or you could think of that as 1 over x divided by negative 1 over x squared. How do you divide fractions? So do 1 over x times negative x squared over 1. So we get a negative x out of all of this. So as x approaches 0 from the right, this is going to and just plug it in. So if it's 0 times infinity, we have to write it as a fraction. And that's probably going to have to be where we stop today. Tomorrow we're going to talk about differences and powers and their indeterminate forms. So if you're going to be gone, you definitely want to watch the video tomorrow. I am going to go ahead and give you some homework